Welcome to today's session. In this video, we will be tackling the problem number 1218, longest arithmetic subsequence of given difference. This is a fascinating problem that combines dynamic programming concepts with hash map utilization. Let's dive in and explore how we can solve this step by step. In this problem, we are tasked with finding the length of the longest arithmetic subsequence in a given integer array ARR that has a specified difference. A subsequence is a sequence that can be derived from the array by deleting some or no elements, while keeping the order of the remaining elements unchanged. For example, in the array 1, 2, 3, 4, 1, 3, 4 is a subsequence, but 3, 1, 4 is not, as the order is altered. Now, an arithmetic subsequence is one where the difference between consecutive elements in the sequence is constant, and in this case, the difference must equal the given difference value. The goal is to determine the maximum length of such a subsequence that can be formed from ARR. Let's also clarify the input and output formats to better understand the problem. The input consists of an integer array ARR, where the length is between 1 and 100,000, and each element of the array falls within the range of -10,000 to 10,000. Additionally, a second input difference is given, which can range from -20,000 to 20,000. The output will be a single integer representing the length of the longest arithmetic subsequence with the specified difference. Let's look at an example to make this more concrete. Suppose we have the input array ARR equals 1, 2, 3, 4, and difference equals 1. In this case, the entire array itself forms an arithmetic subsequence where each consecutive pair of elements has a difference of 1. For example, 2, 1 equals 1, 3, 2 equals 1, and 4, 3 equals 1. Since the entire array satisfies the condition, the length of the longest arithmetic subsequence is 4. Now, consider another example with the input ARR equals 1, 3, 5, 7, and difference equals 1. Here, no two elements in the array have the required difference of 1. The differences between consecutive elements in the array are 2, but not 1. Therefore, the longest arithmetic subsequence in this case consists of any single element, and the output is 1. Next, let's examine a slightly more complex example. If ARR equals 1, 5, 7, 8, 5, 3, 4, 2, 1, and difference equals -2, the goal is to find the longest subsequence where consecutive elements have a difference of -2. In this case, the longest arithmetic subsequence is 7, 5, 3, 1. Each pair in this sequence satisfies the condition 5, 7 equals -2, 3, 5 equals -2, and 1, 3 equals -2. The length of this subsequence is 4, so the output is 4. This example highlights that the required subsequence doesn't have to include all elements of the array, and the order of elements in the subsequence must follow their original order in the array. To wrap up the problem statement, let's go over some important constraints and edge cases. First, the array can contain up to 100,000 elements, so the solution must be efficient to handle large input sizes without exceeding the time limit. For example, a simple brute force approach that examines all possible subsequences would likely be too slow. Second, if the array contains only one element, the longest arithmetic subsequence is just that element itself, and the output is 1, regardless of the difference. Third, when no two elements in the array have the given difference, the result is also 1, as the longest subsequence is any single element. Lastly, the problem requires handling negative differences correctly and ensuring that the solution accounts for the full range of input values. Together, these constraints and edge cases guide us to think about efficient ways to solve the problem while covering all scenarios. To begin, let's consider the brute force approach to solving this problem. The intuition here is straightforward. We can form subsequences by iterating through every possible subset of the array and checking if they satisfy the arithmetic difference condition. For each subsequence, we calculate the difference between consecutive elements and count the longest valid sequence. To implement this, we would use nested loops to generate all possible combinations of elements and validate whether each subsequence has a constant difference equal to the given value. However, this approach has significant downsides. Its time complexity is exponential, 2 to the power of n, because we need to generate all subsequences, and depending on the implementation, its space complexity ranges from O1 to O(n). This makes it computationally infeasible for larger arrays, especially when n can go up to 10 to the power of 5. Hence, while conceptually simple, this approach is not practical for solving the problem efficiently. Now, we can improve upon the brute force approach by introducing dynamic programming with nested loops. The idea here is to store the length of the longest subsequence ending at each index of the array. For each element at position I, we look at all prior elements at positions j, where j is less than I. If the difference between ARR I and ARR j equals the given difference, we update the dp table to reflect the longest subsequence ending at I. Specifically, we define dp I as the length of the longest subsequence ending at index I. Using nested loops, for each I, we iterate through all j less than I to update dp I. While this is an improvement over brute force, reducing the time complexity to O n squared, and the space complexity to O n, it is still inefficient for larger arrays due to the nested iteration over prior elements. This motivates us to explore a more optimized solution. To address the inefficiencies of the nested loop DP approach, we turn to an optimized dynamic programming strategy that leverages a hash map. Instead of tracking all indices, the intuition is to use a hash map to store the maximum length of subsequences for specific values. For each element in the array, we calculate what the previous element in the sequence should be, which is the current element minus the given difference. Using the hash map, we can directly determine the length of the subsequence ending with that previous element, if it exists, and then update the hash map for the current element accordingly. Specifically, we maintain a hash map where dp x represents the length of the longest subsequence ending with x. For each number in the array, if number difference exists in the hash map, we update dp number to be dp number difference plus 1. Otherwise, we initialize dp number to 1. Throughout this process, we track the maximum length of any subsequence. This approach is highly efficient, with a time complexity of O n and a space complexity of O n, making it well suited for large input sizes. The chosen strategy for solving this problem is the optimized dynamic programming approach with a hash map. This method stands out for its simplicity, efficiency, and scalability. The key insight here is that we can eliminate redundant computations by using the hash map to directly store and retrieve the lengths of subsequences for specific values. This avoids the nested loops required in prior approaches, reducing the time complexity to linear. The problem naturally lends itself to a dynamic programming solution because it can be broken down into smaller overlapping subproblems, such as finding the longest subsequence ending at each element. The hash map further enhances efficiency by enabling constant time lookup and update operations. With this combination of techniques, the solution is highly scalable, making it ideal for constraints where the array size can be as large as 10 to the power of 5. Finally, it's important to consider the trade-offs and comparisons among the different approaches. While the brute force and nested loop DP methods are conceptually clear, they are impractical for large arrays due to their exponential and quadratic time complexities, respectively. On the other hand, the hash map-based dynamic programming approach achieves significant time efficiency, reducing complexity to linear. The trade-off here is the additional space required for the hash map, which scales proportionally to the size of the array. However, this trade-off is acceptable given the dramatic reduction in computation time. In conclusion, the optimized approach strikes the best balance between time and space efficiency, making it the most suitable solution for this problem within the given constraints. To solve this problem, we need to identify the longest arithmetic subsequence within a given array. An arithmetic subsequence is formed when the difference between every pair of consecutive elements remains constant. The input is an array of integers, and the goal is to determine the length of the longest subsequence that satisfies this property. However, given that the array can have up to 10,000 elements, we cannot afford to use a brute force approach due to its inefficiency. Instead, we use dynamic programming with hash maps. The key insight here is that for any two indices in the array, the difference between their values can serve as a unique identifier for the subsequence they belong to. By storing and updating the lengths of these subsequences in a structured way, we can efficiently solve the problem in a scalable manner. To implement this, we first initialize a dynamic programming table, represented as a list of dictionaries called DP. Each dictionary at index j will track the lengths of subsequences ending at that index for various arithmetic differences. For example, if a subsequence ending at index j has a difference of 3, the dictionary will store the length of that subsequence under the key 3. We also initialize a variable max_length to 1, which will keep track of the longest subsequence length encountered so far. Next, we iterate through the array, and for each element at index j, we compare it with all previous elements at indices I. For each pair, we calculate the difference diff equals arr j arr I. If this difference already exists in the dictionary for index I, it means we can extend the subsequence ending at I. We update the dictionary at j by increasing the length of the subsequence by 1. If the difference does not exist, we start a new subsequence of length 2. Throughout this process, we continually update max_length to reflect the longest subsequence found so far. This approach also handles edge cases, such as arrays with fewer than 2 elements, where the answer is simply the array's length, or arrays with identical elements, where the entire array forms a valid subsequence. Finally, once we've iterated through the entire array and updated the dynamic programming table, the result is simply the value of max_length. This represents the length of the longest arithmetic subsequence found. The key insights that make this approach efficient are worth emphasizing. First, we avoid brute force methods, which would involve generating all possible subsets. This is computationally infeasible for large inputs. Instead, we focus on the property of constant arithmetic differences, which allows us to reduce the problem to pairwise comparisons. The problem also exhibits optimal substructure, meaning that the solution to the overall problem can be built incrementally by solving smaller subproblems for earlier indices. Using hash maps allows us to efficiently store and retrieve subsequence lengths based on their differences, and the overall space required is proportional to the size of the array squared, which is manageable for the given constraints. The core data structures used in this algorithm are the dynamic programming table and hash maps. The DP table is implemented as a list of dictionaries, where each dictionary at index j tracks the lengths of subsequences ending at that index for various differences. This structure ensures constant time access for updates and queries. The hash maps within the DP table use differences as keys and subsequence lengths as values, allowing us to efficiently manage and extend subsequences based on their arithmetic properties. In terms of complexity, the time required is O(n²), because we compute differences for all pairs of indices. The space complexity is also O(n²), due to the storage requirements of the DP table. While this might seem expensive, it is significantly more efficient than a brute force approach, which would involve exponential time complexity. To solidify our understanding, let's walk through an example. Consider the input array 3, 6, 9, 12. We start with an empty DP table. For the first pair of indices, j equals 1 and I equals 0, the difference is 3. Since this difference doesn't exist in the dictionary for index 0, we initialize a new subsequence with length 2 at dp 1, 3. Next, for j equals 2, we compare it with all previous indices. For I equals 0, the difference is 6, so we start another new subsequence. For I equals 1, the difference is 3, which already exists in dp 1. We extend the subsequence by updating dp 2, 3 to 3. Following this process for all indices, we eventually find that the maximum length of any subsequence is 4. In the edge case where all elements are identical, such as 1, 1, 1, 1, the entire array forms a valid subsequence, and the result is simply the array length, which is 4. This example demonstrates how the algorithm efficiently tracks and updates subsequences using the DP table and hash maps. This implementation solves LeetCode problem number 1218, longest arithmetic subsequence of given difference, using a dynamic programming approach with a dictionary for efficient state tracking. ### line-by-line explanation. 1. Initialization of DP dictionary. The DP dictionary stores the length of the longest arithmetic subsequence ending with each number in the array. For example, DP number represents the length of the subsequence ending with number. 2. Tracking the maximum length. Max_length is used to record the longest subsequence length encountered during the iteration. 3. Iterating through the array. The for loop iterates over each number in the input array ARR. For each number, it calculates the previous number in the desired arithmetic subsequence, previous equals number difference. If previous exists in DP, it means we can extend the subsequence ending at previous by including the current number, so DP number is updated to DP previous plus 1. If previous is not in DP, the current number starts a new sequence, so DP number is initialized to 1. For updating maximum length, after updating DP number, the max_length variable is updated to ensure it always holds the length of the longest subsequence found so far. 5. Returning the result. After processing all numbers in the array, max_length is returned as the final result. Key advantages. Efficiency. The algorithm runs in O(n) time complexity, where n is the size of the input array, as each number in the array is processed exactly once. The dictionary operations, lookup and update, are O(1) on average. Space optimization. The DP dictionary only stores relevant states, making it memory efficient. Edge case handling. If the array is empty, the result would naturally be 0, as no subsequences exist. The algorithm handles arrays with duplicate numbers or numbers with no valid arithmetic subsequences correctly, as each number is processed independently. This solution is robust, efficient, and suitable for handling the constraints of the problem, including large input sizes up to 10 to the power of 4 elements. This is the Java implementation of the LeetCode problem number 1218, longest arithmetic subsequence of given difference. The logic mirrors the Python solution, utilizing a hash map to store the length of the longest arithmetic subsequence ending at each number. Key differences include explicit type declarations, the use of Java's hash map for the DP dictionary, and the syntax differences between Java and Python. The algorithm iterates through the array, computes the number needed to extend the sequence, and updates the map accordingly. The time complexity is O(n), where n is the length of the array, as each element is processed once. Let's start with the first example, where the array is 1, 2, 3, 4, and the difference is 1. We begin by initializing two variables, DP, an empty dictionary that will keep track of the length of the longest arithmetic subsequence ending at each number, and max_length, which will store the maximum length found so far. Now, for the first number, 1, we calculate the previous number in the sequence using number difference, which gives 0. Since 0 is not in DP, we know no subsequence ends with 0, so we start a new subsequence with 1 and set DP 1 to 1. We then update max_length to be the maximum of its current value in DP 1, which is 1. Moving to the second number, 2, we calculate the previous number as 2 1 equals 1. This time, 1 is in DP, so we extend the subsequence ending at 1 by adding 2, and set DP 2 to DP 1 plus 1, which is 2. Again, we update max_length, which becomes 2. At this point, our DP dictionary is 1, 1, 2, 2, and max_length is 2. For the third number, 3, the previous number is calculated as 3 1 equals 2. Since 2 is in DP, we extend the subsequence ending at 2 by adding 3, updating DP 3 to DP 2 plus 1, which is 3. We then update max_length to 3, as it is now the longest subsequence length. Finally, for the fourth number, 4, we calculate the previous number as 4 1 equals 3. Since 3 is in DP, we extend the subsequence ending at 3 by adding 4, setting DP 4 to DP 3 plus 1, which is 4. We update max_length to 4, which is the length of the entire sequence. At the end, our DP dictionary is 1, 1, 2, 2, 3, 3, 4, 4, with a max_length of 4. The output for this example is 4, matching the length of the longest arithmetic subsequence with a difference of 1. Now, in the second example, the array is 1, 5, 7, 8, 5, 3, 4, 2, 1, and the difference is -2. Again, we initialize DP as an empty dictionary and max_length as 0. For the first number, 1, we calculate the previous number as 1 minus 2 equals 3. Since 3 is not in DP, no subsequence ends with 3, so we start a new subsequence with 1 and set DP 1 to 1. Max_length is updated to 1. For the next number, 5, the previous number is 5 minus 2 equals 7. Since 7 is not in DP, we start a new subsequence with 5, setting DP 5 to 1, and max_length remains 1. Similarly, for 7 and 8, their previous numbers are not in DP, so we initialize DP 7 and DP 8 as 1, with no change to max_length. When we encounter 5 again, the previous number is 5 minus 2 equals 7, which is in DP. This allows us to extend the subsequence ending at 7 by adding 5, and we set DP 5 to DP 7 plus 1, which is 2. Max underscore length is updated to 2. Next, for 3, the previous number is 3 minus 2 equals 5, and since 5 is in DP, we extend the subsequence ending at 5 by adding 3, setting DP 3 to DP 5 plus 1, which is 3. Max underscore length becomes 3. Continuing with the same example, for the number 4, the previous number is 4 minus 2 equals 6. Since 6 is not in DP, no subsequence ends with 6, so we start a new subsequence with 4, setting DP 4 to 1, and max underscore length remains 3. For 2, the previous number is 2 minus 2 equals 4, which is in DP, so we extend the subsequence ending at 4 by adding 2, setting DP 2 to DP 4 plus 1, which is 2. Max underscore length remains 3. Finally, for the last number, 1, the previous number is 1 minus 2 equals 3, which is in DP. This allows us to extend the subsequence ending at 3 by adding 1, and we set DP 1 to DP 3 plus 1, which is 4. Max underscore length is updated to 4. The output for this example is 4, as the longest arithmetic subsequence consists of the numbers 5, 3, 1, and its length is 4. Finally, in the third example, the array is 3, 0, minus 3, minus 6, minus 9, and the difference is minus 3. As before, we initialize DP as an empty dictionary and max underscore length is 0. For the first number, 3, the previous number is 3 minus 3 equals 6. Since 6 is not in DP, we start a new subsequence with 3, setting DP 3 to 1, and max underscore length is updated to 1. For the next number, 0, the previous number is 0 minus 3 equals 3, which is in DP. This allows us to extend the subsequence ending at 3 by adding 0, and we set DP 0 to DP 3 plus 1, which is 2. Max underscore length is updated to 2. For minus 3, the previous number is dash 3 minus 3 equals 0, which is in DP. We extend the subsequence ending at 0 by adding minus 3, setting DP dash 3 to DP 0 plus 1, which is 3. Max underscore length becomes 3. For minus 6, the previous number is dash 6 minus 3 equals dash 3, which is in DP, so we extend the subsequence ending at minus 3 by adding minus 6, setting DP dash 6 to DP dash 3 plus 1, which is 4. Finally, for minus 9, the previous number is dash 9 minus 3 equals dash 6, which is in DP. We extend the subsequence ending at minus 6 by adding minus 9, setting DP dash 9 to DP dash 6 plus 1, which is 5. Max underscore length is updated to 5, and the output for this example is 5, as the longest arithmetic subsequence consists of 3, 0, minus 3, minus 6, minus 9. The time complexity of this solution is O, n, where n represents the length of the input array. This is because the algorithm iterates through the entire array once in a single loop, making the iteration itself an O, n, operation. Additionally, for each element in the array, we perform dictionary operations. These include checking if a previous element exists in the dictionary and updating the dictionary with the current element. Both of these operations, dictionary lookup and insertion, are O1 on average due to the underlying hash table implementation in Python. Since these dictionary operations are performed once per element, their total contribution is O(n) asterisk O1, which simplifies to O(n). Thus, combining the loop iteration and dictionary operations, the overall time complexity of the algorithm is O(n). The space complexity of this solution is O(n) in the worst case. This is primarily due to the dictionary DP, which stores the lengths of the longest arithmetic subsequences ending at each element in the array. In the worst-case scenario, where all elements of the array are unique, the dictionary will contain one entry for each element, resulting in n key-value pairs. Hence, the space used by the dictionary is O(n). Besides the dictionary, the algorithm uses a few auxiliary variables such as max underscore length, number, and previous, whose space requirements are constant, or O1. When we add these together, the overall space complexity is dominated by the dictionary, leading to a total space complexity of O(n). In terms of best, average, and worst-case analysis, the algorithm consistently requires iterating through the entire array, so the time complexity remains O(n) across all cases. The space complexity is also O(n) in all cases, as the dictionary may store up to n elements when all elements in the array are unique. Comparing this to a naive approach highlights the optimization. A naive solution would involve generating all possible subsequences of the array, which takes O(2 to the power of n) time. Verifying the arithmetic property for each subsequence adds further overhead, making the naive approach computationally infeasible for large inputs. This exponential complexity starkly contrasts with the efficient O(n) time and space complexity of the optimized solution. The optimized approach leverages dynamic programming and a dictionary to significantly reduce computational overhead. By storing intermediate results in a dictionary, the algorithm avoids redundant calculations. The single loop processes the array in O(n) time, and the constant time dictionary operations, such as lookup and update, contribute O(1) on average for each element. This results in a total time complexity of O(n). Space complexity is driven by the dictionary, which may store up to n elements in the worst case, leading to O(n) space usage. The mathematical proof for big O can be summarized as follows. The loop iterates n times, and dictionary operations contribute O(n) overall, while space requirements are proportional to the number of dictionary entries. Thus, the algorithm achieves optimal time and space complexity of O(n). When solving this problem, there are some common pitfalls to avoid. First, it's important to distinguish between subarrays and subsequences. Subarrays are always contiguous sections of the array, while subsequences preserve the order of elements but can skip numbers in between. Confusing these concepts can lead to solutions that don't actually meet the problem's requirements. Additionally, edge cases are critical. For instance, arrays with fewer than 2 elements or arrays where every element is identical might behave differently than expected, and failing to account for these can result in runtime errors or incorrect outputs. Another frequent mistake is relying on brute force solutions, such as generating all possible subsequences, which has exponential complexity. This approach might work for very small inputs but will fail to scale for larger arrays. Finally, remember that the arithmetic difference must remain constant throughout the subsequence. If this isn't enforced, you risk accepting invalid solutions that don't follow the problem's constraints. Now, another issue to watch out for is the role of sorting. Some optimized approaches, particularly those involving arithmetic progressions, can depend on sorting the array first. Skipping this step, if the method requires it, can lead to incorrect results or missed opportunities for optimization. From an interview perspective, there are a few key insights to keep in mind. Recognizing patterns in the problem is crucial. Subsequence problems often lend themselves well to dynamic programming, hashing, or sorting. Understanding which approach fits best depends on the constraints you're working with. It's also a good idea to start with a simple brute force approach to clarify the problem, but you should quickly identify its limitations and pivot to optimized solutions. Test cases are especially important. Be sure to test edge cases like empty arrays, arrays with identical elements, or very large inputs to ensure your solution is both correct and efficient. Finally, always consider the trade-offs between time and space complexity. For example, dynamic programming solutions often use more memory to achieve faster runtimes. This problem also connects to several related problems that can help you deepen your understanding of similar concepts. Problem 1027, the longest arithmetic subsequence, is a classic example that focuses on finding the longest subsequence with a consistent difference, much like this one. Problem 300, the longest increasing subsequence, is another variation but focuses on maintaining an increasing order instead of a fixed difference. Problem 674, the longest continuous increasing subsequence, shifts the focus to subarrays instead of subsequences, meaning it requires contiguous segments. Finally, the problem at hand, 1218, is a more specific version of the arithmetic subsequence problem, as it constrains the difference to a fixed value. These variations highlight how small changes in constraints can lead to different problem-solving strategies. To solve this problem efficiently, you can explore several alternative approaches. Dynamic programming is a powerful technique here. By using a DP table, such as a dictionary that maps value difference pairs to subsequence lengths, you can keep track of your progress effectively. While this reduces complexity to O(n squared), it does come with increased memory usage. Hashing offers another efficient solution. By using a hash map to store the lengths of arithmetic subsequences with specific differences as you iterate, you achieve a similar complexity of O(n squared), but this method is often faster in practice due to reduced overhead. Sorting combined with binary search is another option. Sorting the array first simplifies identifying valid subsequences, though it does add an O(n log n) overhead. Lastly, in certain variations, greedy algorithms can provide a faster solution by directly constructing subsequences based on specific criteria, like the smallest or largest elements. However, greedy methods are generally less flexible when dealing with arbitrary constraints, so their use depends on the specific problem context. Great work on completing this problem. To summarize, we used a dynamic programming approach with a hash map to solve this efficiently in O(n) time. Remember, mastering hash maps in dynamic programming is key for tackling similar challenges. Thanks for watching, and don't forget to like, subscribe, and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!